In this lesson, we shall be learning about how we can affect the position of an equilibrium, how we can either shift an equilibrium to the right to favor the products, or we can shift it perhaps backwards also to favor the reactants. This is possible if we vary certain conditions such as temperature and pressure. Let's now go on to the next slide where we look at the specific METSEC assessment criteria that we shall be dealing with through this presentation. So in this video lesson and presentation, we shall be discussing principally 12.3D, which is the assessment criteria, which is mainly about how changing factors to an equilibrium, changing the factors of an equilibrium rather, such as pressure and temperature, will result in a shift in the position of the equilibrium. We shall also, in the last part of this presentation, introduce the Haber process or the Haber process. In the Haber process, which is the industrial production of ammonia with the purpose of using the ammonia mainly for the production of fertilizers, explosives, and also other chemicals in the chemical industry, we shall be focusing on the conditions that best give us the optimum yield of ammonia, okay? Since the Haber process is an equilibrium where you have nitrogen and hydrogen on the left, giving us ammonia on the right. We shall see how industrial chemists promote the forward reaction of the equilibrium in order to maximize the yield of ammonia gas. But more of that when we come to the final part of the presentation. Let's now move on to the first factor that we should consider when talking about an equilibrium, and it is when we add a catalyst. Does this have any effect on the position of equilibrium? That's what we are about to find out. The first thing I really want to point out is this: adding a catalyst will not shift the position of an equilibrium. If you would have obtained an 80% yield of product, okay, that 80% yield will stay there whether you have a catalyst or not. The catalyst will, however, speed up the rate at which you obtain that 80% yield of product. Okay, so it will speed up the reaction in order to make it economically feasible. Now, let's clarify all of this with the graph that there is right above me. Now, let's focus first of all on the gray lines of the plot. Okay, so on the y-axis, I'll use a pen to better explain myself, and perhaps a black pen would be best since we have red lines already on the curve. So note that on the y-axis the unit is moles per liter, and we are measuring concentration. It could be concentration of the reactants or concentration of the products. We are plotting them on the same axis. Note that the time is being recorded in hours, so this is a long-term reaction. Okay, typically laboratory reactions that we use with students are in seconds, mainly in seconds, perhaps most in minutes. Okay, I want you to focus on the gray lines, on the solid gray line, which is this line going upwards, and on the dotted gray line, which is going downwards. The dotted gray line and the solid gray line represents the reaction without the addition of the catalyst. How can I say this? Because notice the gradient is shallow. Okay, so if I had to draw the gradient at this point, it's quite a shallow gradient. If I had to compare it with the catalyzed reaction, which I shall be speaking of in a moment, but the catalyzed reaction is the dotted line, the red dotted line. Notice how far steeper the gradient is. Okay, so notice what happens to the gray plot, the solid gray plot, which represents the rise in the products from 0 at the start of the reaction. As you might expect, there are no products at the very start of the reaction, but these rise quite rapidly, even in the uncatalyzed reaction, which is represented by the solid gray line. Eventually, at equilibrium, you have no more of the product increasing beyond a certain point. More of the product is being made, but it is exactly being balanced out by the amount of product that is breaking down to reform the reactants. So I'll clarify. We are still getting product being formed from this point moving forward, but that product is breaking down to reform the reactants. Okay, that is the equilibrium position, as we also discussed in the previous presentation. Notice that for the reactants, the dotted gray line, which is that line, represents the uncatalyzed reaction. The gradient is not so steep, and the reactants, as might be expected, start off at a high concentration. The concentration fairly rapidly drops off, since there are lots of reactant particles at the start of a reaction. That gradient will start to become more and more shallow as the reaction proceeds, because less and less reactant particles are available for reaction. Eventually it levels out and there is no observable change on the macro scale. If I had to take a snapshot, okay, it's as if I have a big view of the whole picture, I would not see any change in reactants. It does not mean that the reaction has stopped. What it means is that so many particles of reactants are forming the products, and the products are reversing back to form the same number of reactants that changed into the product. So the forward and the backwards reaction are at the same rate. Now, what we're mostly interested in is the red plots. Without scribbling any further on that graph, because otherwise it will get too confusing, I want you to take particular note of the solid red line, which represents the rise in the products for the catalyzed reaction, and compare it to the dotted red line, which represents the drop in the concentration of reactants for also the catalyzed reaction. Note that both for these red lines, for both the red lines, the red line for the product and the red line for the reactants, the gradients are steeper than for the gray lines. The red lines show us the rate at which equilibrium is reached for the catalyzed reaction. The product concentration, the maximum product concentration, is reached faster in the catalyzed reaction. The red line, the red solid line rising to the leveling off of the product is steeper than the gradient you have for the solid gray line, which shows the rise in concentration of the products, but for the uncatalyzed reaction. Likewise, if you look at the reactants, the dotted red line shows you that for the catalyzed reaction, the drop down, the drop off in the concentration is steeper than for the dotted gray line, which represents the drop off in the reactant concentration, but for the uncatalyzed reaction. So, summarizing what we have on this slide, summarizing what we have in the graph. For a catalyzed reaction, the state of equilibrium, of dynamic equilibrium, is achieved faster. If the original state of equilibrium was shifted over to the right to give us, for example, 70% yield of product, exactly that same position of equilibrium to give us 70% of the product is again given to us by the catalyst. There is no change at all in the position of the equilibrium. However, as we have just discussed, instead of taking, for example, 10 hours to reach that state of equilibrium, it is reached much faster. Say, for example, in 15 minutes. Okay, I'm not exaggerating, by the way. When a catalyst is used, the order of magnitude by which the reaction is accelerated is pretty vast. Okay, let's take, for example, a laboratory-based reaction, which you are familiar with. If you are talking about hydrogen peroxide, all right, I'm not now, forget whether it's reversible or not. It's not actually reversible in the true sense of the word, because the hydrogen peroxide is decomposing to give you water and oxygen, and the oxygen is escaping. It's not even a closed system, so it can never be a reversible reaction in that respect. But we're not interested in that. All we're interested in at this point is what the catalyst does to the rate of reaction. In that particular instance, which you already saw in your syllabus, if you had just opened the bottle of hydrogen peroxide, you would have left it for a long time without seeing any effect at all. Okay, it is not visible, okay, to the naked eye in that way. But if you had to add just a little amount of the catalyst of choice, which is manganese dioxide, you would immediately see that colorless, odorless, vigorous effervescence. Okay, so keep in mind that a catalyst will have no effect on the position of the equilibrium. All it does is it will accelerate the rate at which the position of equilibrium is achieved. Let's now move on to the next slide. This slide is just a concluding remark to my previous slide, where I discussed at length about the addition of a catalyst to an equilibrium. As the cartoon shows you, the catalyst, as we already said, has absolutely no effect on the position of the equilibrium. You don't form more of the product because of the presence of a catalyst. Okay? The only thing that the catalyst does, it will give you the same amount of product as the uncatalyzed reaction, and it will give it to you faster. If you had to look at the graph, which is right above me, I need you to focus on the blue and yellow solid curves, okay? On the blue and yellow solid curves. The blue solid curve represents the forward rate of reaction. How do I know it's the forward? Because we start off with a fast rate, okay? How do I know it's a fast rate? It's high up on the y-axis. And since it's the fast rate, it's because there are a lot of reactant particles reacting together to give us the products. That is the forward reaction. As more and more time passes, less and less reactant particles are available, and so what happens is that the gradient starts to level off. Eventually at equilibrium it evens out completely. So on the macro scale it looks as if, but it's not the case as we explained, it looks as if the reaction has stopped. But of course it is only in equilibrium. Okay? The rate of the forward and backward reaction are identical. How can I see this on the graph? Notice the yellow solid line shows us the backward rate of reaction. And at first, at time zero, the backward rate of reaction is zero Because there are no products yet formed, so there are no products to give you back any of the reactants. As more and more time passes, product starts to form. As soon as product starts to form, it starts to give you a backward reaction. And why is this? Because now you have product particles available to react and to give back the reactants. Eventually, the rate of the forward and the backward reaction are identical, and we say that a steady state of dynamic equilibrium has been achieved. Now, in order not to complicate and to finalize the explanation on this slide, compare the solid blue and yellow lines with the dotted blue and yellow lines. Note that in the dotted blue line, which represents the forward rate catalyzed, the gradient is much steeper and the equilibrium position is reached already at this point. Compare that point to this point for the uncatalyzed reaction. So the catalyst will allow the equilibrium position to be achieved faster. Also notice that the products are produced at a faster rate and they also come into equilibrium so much faster. Let's now move on to the next slide. We shall now speak about the effect of pressure on the position of an equilibrium. Now, unlike a catalyst, changing the pressure can change the position of an equilibrium. And I shall explain it as simply as I can, okay, using the example that we have over here, the reaction between carbon monoxide gas and hydrogen gas to give us methanol, okay? Just for your general knowledge, the mixture of carbon monoxide gas and hydrogen gas has been referred to in the past as synthesis gas. Now what I want you to note is this, that the reaction is balanced, okay, as you can note. Check this out for yourself. So it means that we have 1 mole of carbon monoxide. It's important that you revise your calculations in chemistry, okay? Reacting with 2 moles of hydrogen gas, and they will give us 1 mole of methanol. Now you might feel a bit uncomfortable with this because methanol is encountered as a liquid in everyday life, okay? But however, it is a very low boiling point liquid. So at the temperature at which it's produced by means of this chemical reaction, it would be in the gaseous form, okay? Methanol is also a constituent of the familiar purple methylated spirits that are used as a camping fuel, for example, or as a cleaning solvent, okay? Now, let's focus on the reaction. So we have on the left-hand side 3 moles of gases in all. 1 mole of carbon monoxide added on to 2 moles of hydrogen gas. Also, as you can see from the picture right on top of me, okay, which clarifies this in a diagram form. Note that these 3 moles of gas are combining all together and forming just 1 mole of gaseous methanol, okay? Now, nature is, let's call it, lazy. It doesn't like to change. It tends to oppose an external change. Let's imagine the situation where this chemical reaction, I'm inventing numbers, takes place at a pressure of 1 atmosphere. Imagine that we have this reaction taking place at a pressure of 1 atmosphere. Would there be a change to the position of the equilibrium if I had to increase the pressure to, say, 5 atmospheres? Okay, so what do I mean by this? In other words, when I say, is there a change in the position of the equilibrium? Is the equilibrium pushed forward to the right to favor the production of methanol, or is it, on the other hand, being pulled back to the left to favor the production of carbon monoxide and hydrogen? In other words, is it favoring the backward reaction? Now let's use the logical argument I have just presented, that nature resists a change. So, in the reaction as observed, 3 moles of gas give us 1 mole of product. If I were to increase the pressure, okay, what would happen is that the equilibrium doesn't like this change. Okay, I'm using these terms to help you understand, okay? The equilibrium is not a human being, so it cannot like or dislike anything, but it's easier to explain in this way. So, I'll repeat myself. If I were to increase the pressure from 1 atmosphere to 5 atmospheres, okay, the equilibrium doesn't want to experience this pressure. It tries to get rid of this pressure. How can it get rid of the pressure? By favoring the forward reaction or the backward. It tends to favor the forward, because by moving forward, it's converting 3 moles of gaseous particles to just 1 mole. And having 1 mole of gaseous particles will mean that you have lesser collisions, and lesser collisions per second means lesser pressure. You have lesser collisions between the particles themselves and between the walls of the container. So decreasing the number of particles is what the reaction does in order to counteract, to go against, to oppose your pressure increase. In other words, the equilibrium shifts forward, more of the products are made than when compared to the condition of 1 atmosphere, when there was a lower pressure. So an industrial chemist could, in other words, trick the equilibrium to shift forward and produce more of the product that he or she wants by increasing the pressure. And this is what industrial chemists do. They find out those conditions of temperature and pressure that best favor the production of the material that they want to sell, that they want to produce. Okay, now in this case, we want to produce methanol. So pressure-wise, this reaction would probably take place at quite a high pressure. Okay, I have invented the numbers, 1 atmosphere and 5 atmospheres. Okay, you could check out for yourselves the actual working conditions for this reaction. Okay, let's now move on to our next slide. So this is a further example of the effect of pressure on the position of an equilibrium. Now, let's consider the reaction whereby nitrogen dioxide, okay, forms dinitrogen tetroxide. Dinitrogen tetroxide, as the name implies, is N2O4. Dinitrogen, 2 nitrogens, tetroxide meaning you have 4 oxygens. Now, in terms of pressure, what is important is always to note the moles of reactants and products. So, starting from the left-hand side, we have 2 moles of nitrogen dioxide, and on the right-hand side, we have just 1 mole of dinitrogen tetroxide. Okay? Using the same argument that I used previously, when I said that nature hates a change and will try to oppose the change. In other words, the chemical reaction. When I speak of nature, I'm speaking of a chemical reaction, okay, to be more specific. So, if I had to use a higher pressure, okay, what happens is that the system, the chemical reaction, tries to oppose the higher pressure, okay, And how can it oppose the higher pressure? By forming more of the dinitrogen tetroxide or more of the nitrogen dioxide. I've actually put it in as a question right above me. Now, since this is a recorded lesson, I will have to answer it myself, but you can pause it right now, think about it, and then check whether what you think is what I'm about to say now. What I'm about to say now is this. If I had to increase the pressure, okay, of the reaction, since the system wants to get rid of that pressure, it can do so by favoring the forward reaction. Why is this? Because by moving forwards, we move from 2 moles of gases, 2 moles of nitrogen dioxide, to just 1 mole of dinitrogen tetroxide. In other words, the extra pressure can best be relieved by moving forward. The system is trying to bring the pressure down again. So in other words, we are producing more of the dinitrogen tetroxide because the system shifts over to the right in favor of the products. And if you want to form more of dinitrogen tetroxide, increasing the gaseous pressure is one of the ways in which you can do so. Let's now move on to our next slide. We shall now consider the reaction of nitrogen dioxide and dinitrogen tetroxide, but in reverse. Imagine we started off with dinitrogen tetroxide and we ended up with nitrogen dioxide, as indicated in this chemical equation over here. Now, let's first consider the colors. Dinitrogen tetroxide is a dimer. It is, if you like, 2 nitrogen dioxide molecules connected together, which when they connect together, they become a colorless gas, and the colorless gas is called dinitrogen tetroxide. If you had to change dinitrogen tetroxide back to nitrogen dioxide, you should remember also from your year 9 chemistry, when you were talking about air pollution, you would have noted at one point that nitrogen dioxide, which is a gaseous air pollutant, okay, is a brown gas, okay? So you can observe also the extent of the forward reaction and the backward reaction even by color. It can be used as an indication. If you have a really dark brown color, it means that you have a lot of nitrogen dioxide. And it does look like your forward reaction could be favored, okay? But if the color of the gas of your gaseous mixture is very close to colorless or colorless, then there is no doubt that it is the reverse reaction and the backward reaction, therefore, that is being favored, okay? And the equilibrium is therefore all over to the left. Now, when we consider the effect of temperature on an equilibrium, we have to get used to 2 words, endothermic and exothermic, and I've underlined them over here, okay, in the first part of our slide, okay? Now, to be fair, you shall be talking about these 2 words more when you discuss energetics, okay, in Learning Outcome 15. Where you will also discuss energy curves, enthalpy curves, and so on. But at this point, it is essential that you have a basic understanding of what they mean. An endothermic reaction is a reaction that takes in heat. And since it takes in heat from the surroundings, okay, it will feel cold to the touch, okay? So if I had to have a reaction container, okay, so let's put it down in this way. Imagine I have a reaction container, and over here I have a reaction mixture where I have an endothermic reaction, and we can abbreviate in that way. If I had to put in a thermometer, okay, in the reaction mixture, the temperature will drop, okay? And the container, if I had to hold the container with my hand, it would feel cool to the touch. So an endothermic reaction takes in heat, okay? And since it's taking in heat, okay, basically it is going to cool down your temperature. If I had to look at the exothermic reaction, it works in the opposite sense. The exothermic reaction releases heat. An excellent example is a neutralization reaction between a strong acid and a strong alkali. It releases heat. And the temperature recorded, if you had to insert a thermometer in an exothermic system, the temperature will rise. Now, just as with the argument about a system hating a change in pressure, a system will also hate, if you like, a change in temperature. Now, the forward reaction, moving from dinitrogen tetroxide to nitrogen dioxide, requires heat. It takes in heat. So it is an endothermic reaction. If I had to increase the temperature of the system, what does the system do? The system tries to remove the heat. How can it remove the heat and cool itself off? By promoting the forward reaction. In other words, the endothermic reaction. On the other hand, if I cool the system by, for example, placing it in ice, the system doesn't want to feel cold. It wants to get back to its original temperature. Okay? How can it get back to its original temperature? By promoting the backward reaction, which is exothermic and releases heat. And since you have a release in heat, the temperature starts to go back up. Notice, if the forward reaction is endothermic and takes in heat, and you have a temperature drop, the reversed reaction, the backward reaction, has to be opposite. It has to be exothermic, and it has to release heat in the opposite way that an endothermic reaction takes in heat. Okay? Let's now move on to the next slide, where I just conclude what I have stated right now on this slide. So this is the concluding remark, as I said in the previous slide, regarding temperature and equilibrium. We have said enough about the equilibrium of dinitrogen tetroxide and nitrogen dioxide with respect to temperature. Let's now get back to our original equilibrium equation, the one where we saw that synthesis gas forms a gaseous methanol. We had spoken of the effect of pressure on that equilibrium. Now we'll see the effect of temperature. So first of all, I need you to focus on the notation that I've got at the right of the equation. And I'm referring to this notation over here, where I have delta H is negative. Now you will see this very much more when you come to do your topic on energetics in METSEC Learning Outcome 15. Okay, but once again, it's necessary that I introduce it at this point. What that means is that moving forward from reactants to products in this direction, the reaction is exothermic. The negative sign means that heat is given out. Exothermic. So if the forward reaction, in this case, moving over from carbon monoxide and hydrogen to methanol, is exothermic and raises the temperature, therefore moving in the opposite direction must therefore be endothermic. And in this case, since it is endothermic, there would be a drop in temperature. By the way, the endothermic reaction would be represented by delta H is plus, okay? So rather than negative, it will be plus, okay? Because it must be opposite to the forward reaction. Now, So, if we want to favor the product, let us say that we are producing methanol and we want to favor the product. How can we play around with the temperature to favor the product? Should I increase the temperature? If I increase the temperature, the system doesn't want that rise in temperature. What does it try to do? It tries to reduce that temperature, but it can't reduce the temperature by moving forward. If it moves forward, since the reaction is exothermic moving forward, it will further increase the temperature, and it will further increase its problem with rise in temperature. What it wants to do is therefore move backward, because when it moves backward, the endothermic reaction removes that extra heat and cools off the system. So if I want to promote the forward reaction and produce more methanol as the gas, what I must do is try to use a lower temperature. If I lower the temperature, the system tries to oppose me. How can it oppose me? By releasing more heat. How can it release more heat? By promoting the forward exothermic reaction, which replaces that heat. So, the equilibrium position in that case is shifted over to the right. Let's now go on to the next slide. So this slide over here is to prepare you for the video, which is on the next and final slide. The video is basically a recap of all we've said so far. Now, just a word of caution. The video presenter mentions Le Chatelier's principle. I haven't mentioned this at any point, but when I said that a system tries to oppose a change, okay, so for example, if I increase the temperature of a system, of a reaction, okay, when I increase the temperature, the reaction tries to move in a way either forwards or backwards that will decrease that temperature rise. Likewise, if I had to change the pressure, perhaps if I had to lower the pressure of a system, then the system would try to increase the pressure. Basically, this is Le Chatelier's principle, which states that a system will try to oppose any change imposed upon it by shifting the equilibrium either to the right or to the left as required. Okay, so basically be aware of this Le Chatelier's principle, okay, when the demonstrator refers to it, because that's what he does first off. The demonstrator explains about the effect of pressure, the effect of temperature, and also the effect of concentration of a reactant or a product, but he refers to a reactant. I have not spoken specifically about it. I shall, if you like, mention something about it over here so that you won't be surprised by what he has to say. Basically, if we had to consider this chemical reaction, okay, which is an equilibrium where A and B are forming C and D. Besides moving around the pressure and the temperature, let's say I wanted to produce more of the products C and D. I could do this by increasing, for example, A. If I increase the amount, the starting amount of A, okay, the system doesn't like that increased amount of A. It tries to remove that increased amount of A. How can it remove that increased amount of A? By shifting the equilibrium to the right. By shifting it to the right, it removes that A and produces more of C and D. Okay? So basically, when the video narrator or demonstrator mentions adjusting concentration, okay, what he is referring to is adjustment of the amount of a reactant. He refers to a reactant. He also speaks about the effect of temperature and pressure on an equilibrium. And I think that by watching the video and by taking note of the learning objectives that I have highlighted over here. Okay, so basically the learning objectives are all that I've explained in the previous slides. You will be, first of all, stating that a chemical equilibrium will tend to oppose a change in pressure, temperature, and concentration. And how can it do this? It either shifts to the right, favoring the forward reaction, or to the left, favoring the backward reaction. You will then be able to apply your knowledge of all of this lesson to the Haber process, which I shall be dealing with in more detail in the next presentation, which will also be the final presentation of this series of lessons. However, it's a good introduction. Basically, the video narrator uses the Haber process to explain how you can change the temperature and pressure to affect the amount of product, which is the amount of ammonia produced. Okay? He shall also speak about how you can change the amount of reactants, also to change the amount of product ammonia. Okay? Well, that is it. Okay? I urge you to go on and to view the video. Okay? And after you have watched the video, okay, return back to this slide and make sure that each of my learning objectives, which I have highlighted over here, you have clearly identified from the video and you have clearly understood them. Thank you for watching this presentation. Now go on to watching the video, and best wishes with your studies in chemistry. Thank you.